Hello, welcome to a presentation and overview of Bijou Electronics' new testing and evaluation metric, Power Quality Score, or PQS. Within this presentation, power quality is going to be defined and described. The reasoning for a more encompassing power quality metric will be given. How much power quality affects the world and what it would be like if it wasn't an issue. The products the metric currently covers will be listed. As of now, this will be dedicated to the smaller power components. Finally, a contact form to get some more information or check out the services offered by Bijou Electronics will be provided. Power quality is simply put a measure of how good power is being used. Everything that plugs into the wall uses some power. Power over time is energy. More power means more energy. The power from the wall is alternating current, or AC power. The components of AC power are voltage, current, phase, and frequency. These are all values derived from physics equations. These four parameters allow real power to be calculated. This also allows determination of energy being lost. If these parameters are out of phase or misaligned or of different frequencies, power and therefore energy is being wasted. It is going to start to get a little bit complicated, and I will be leaving out some information but trying to cover as much as possible here to get a basic understanding of the power usage and quality metrics in alternating current systems. The real power is in watts and is expressed in the graphs with the orange line. This is 100% effectively consumed power with a high power quality. As the phase change gets larger, the power is effectively consumed differently. In this case, the gray line represents a 90-degree phase shift between current and voltage. In the first graph, you can see all components are positive. Current is always moving in all these cases. As you can see in the second graph, gray line, half the power is above zero and half is below. When you average these values, zero real power is consumed. To capture this current that is still flowing in the system, additional terms are used. Apparent power and reactive power combined with real power make up the metrics used to characterize power in AC systems. The ratio of the apparent power to the real power is captured in a metric called power factor. This value goes from -1 to 1. In any power-consuming device, it will be from 0 to 1. Here is some additional detail on power factor. When power factor is 1, the current and voltage are in phase. All the current is effectively being converted into real power. A power factor of 0 means none of the current is being used, but still moving through the circuit and causing real losses. A value of 0 is impossible because of the parasitic losses in real components and wires. A capacitor always has some resistance, and that resistance has some inductance, and that inductance has some capacitance. Harmonics are a complex topic that could have its own entire presentation. The most important piece of harmonic content is that power at a non-fundamental frequency, 50 or 60 Hz, is going to cause extra current losses within a power system. This will lower power factor, power quality, and create additional losses on power supply systems. Harmonic information is captured in a metric called total harmonic distortion, or THD. This can also contain the other information in a spectrum. This will be called noise, or THD plus N. The basic formula is shown, and this essentially boils down to the sum of the amplitudes of the harmonics divided by the amplitude of the fundamental frequency. So again, another ratio. It is multiplied by 100 to make it a percentage. THD can go over 100% though. THDs of 200+% are not uncommon on switching power supplies. The graphs show the typical wave shape for a non-sinusoidal current in a switching power supply input stage. This harmonic real power has a much higher peak current and it consumes it over a very short period compared with the sinusoidal ideal real power case. The main takeaway is that the higher the THD, the worse the power quality. Efficiency is another important metric. The higher the efficiency, the better. Higher efficiency means more of the input power is supplied as output power or power to do actual work. The resistor is an ideal load, as near 100% of the input energy is used. A resistor is also a linear device, which means the current and voltage waveforms look the same. This also means it has very low harmonic content, which means good power quality. A resistor converts power to heat. If the purpose is creating heat, then the power quality is very high. The power consumption is also potentially very high. For this reason, both real power used and the power quality score are presented for all use cases. Power quality score, PQS is a combined metric containing power factor, efficiency or efficacy, and total harmonic distortion. PQS is a single number rating of power quality at each device setting or at several load settings, typically 0, 0.1, 10, 25, 50, 75, and 100% load for a power supply or power adapter. PQS is presented as three highlighted values within the database: idle power quality score and power usage, average power quality score and power usage, and maximum power quality score and power usage. The core data is always available for more analysis. Power quality score, PQS, is a value from 0 to 200. The reason for going to 200 is to provide more detail when comparing products. This helps find differences between various power-consuming devices of similar types, which may bunch up if made with the same basic topology. A great example of this is flyback transformer-based circuits. Here is a basic example logo of an average rating with a barcode link to more information. PQS includes detailed power quality in a simple metric. As stated before, the power consumed is separate from the quality metric. Several modes are combined to provide overall ratings. Why does power quality matter? In short, lower power quality costs money and energy. Low power factor and high total harmonic distortion create extra high currents in a system, which create even more loss. The larger the extra current that flows in the system, the larger the real power losses become, due to the real resistance in components that is unavoidable. Low efficiency products, where the power in is much lower than the power out, means that more heat is created and less real work is being done. This means more power generation is required to do the same amount of work. In the graphs, the leftmost is displaying how the input current changes based on power factor. The lower the power factor, the higher the current. Note the legend on the side of the graph is upside down. The middle graph is showing a percentage of loss for various cases of power factor and input power. At high power factors, the loss is very low, single percentage points, unavoidable due to real system resistance. As the power factor decreases, the losses get worse and worse, until at very low power factors, 100% extra energy is required to do the same work. On the rightmost graph, an estimate of cost per year to cover this low power factor is provided. Notice that at high power factor, the cost is only changing moderately as the power increases. For the power factor 0.35, the curve shape is clearly not linear, and the cost starts to shoot up exponentially as the load increases. 0.35 power factor is an extreme case, but it helps to prove the point that improving power factor has real-world results. Who does power quality affect? Everyone. As we saw on the previous slide, low power quality is directly tied to wasted energy. Extrapolate to a larger scale, only including the USA for now, and we'll see that there is a lot of wasted energy on the table still. Low power quality score, PQS, is directly tied to wasted energy. This wasted energy means power production has to be higher. Wasted energy means higher carbon dioxide output. In this case, at 1 megawatt hour of waste energy per household per year, based on lower power quality score metrics, this equates to 0.709 metric tons of extra carbon dioxide per year. This means 5 very large power plants in the USA worth of wasted energy. All solar production as of 2020 isn't enough to offset the lost energy in low power quality products. People use hundreds of millions of devices every day in the USA alone, most with poor power quality score. Power quality score is designed to be simple and easy to measure. Basically, gather the data of a device over several load conditions or the available operating modes and process that information with the power quality score calculation system. The system then provides the individual metrics for each mode. The most important highlighted items, are idle power and power quality score, average power and power quality score, and maximum power and power quality score. I know this is a lot of numbers, but this data listed in the database gives the industry and consumers an idea of how the product performs under many possible conditions. This data can be used to calculate industry scale and product-specific scale metrics to help people identify weaknesses. Finally, this gives engineers the ability to focus on specific parts of the power quality to know how to improve the product for the future. Many devices are covered by power quality score. In fact, anything could technically be covered. But to keep things simple, the metric is being specifically used for smaller power-consuming devices. A power limit of 2.4 kilowatts or 2.4 kVA is enforced. Some examples of devices that incorporate efficiency as part of the power quality metric are listed on screen. All these devices provide a power in and a power out. Devices of any alternating current voltage can be measured from all over the world. Continuing the list of products, many devices do not incorporate efficiency. These are the end users of electrical power. So here is a long list of products that use the power to do some work. For example, electric power is converted into air moved in the case of a fan, or into light output in the case of a light bulb or lighting fixture. Many other things can be covered by this testing, so feel free to reach out to find out if your product can be covered by the Power Quality Score system. Power quality and power quality score are not a lost cause. Some products have excellent power quality while some don't. The majority sits somewhere in the middle. To improve power quality, the first thing to look at is getting the power factor as close to 1 as possible. By doing this, you improve both the shape of the waveform and the alignment of the current and voltage. The next thing to do is to improve the total harmonic distortion. The closer you get to the same shape as the voltage waveform, the more effectively the power is being used. Finally, improving efficiency or efficacy of the product as much as possible. This should be an obvious one, but does require some explanation. A product could have a great power quality but be 10% efficient, therefore waste most of the incoming energy as heat. Providing as much useful work on the output as possible is the goal. Increasing efficiency or efficacy will lower the real power consumption of a product. So get involved and lower the real power consumption of the product and improve the power quality. Be the class leader of an industry. Thanks for watching and stay tuned for more power quality content. The power quality movement is getting started, with industry rating systems starting to require reporting of more information to give a more complete picture of power usage. The importance of power quality is only increasing as time goes on. If you would like to join the Power Quality program, visit our webpage or contact us at bijouelectronics.com or in the email contact below. Thanks again.